Welcome to section 10.3, which is Apply Properties of Chords. We have three objectives for today's video. The first objective is to use properties of congruent arcs. So we talked about congruent arcs in the last video. Congruent arcs have the same measure and the same radius. Then we are going to determine if a chord is a diameter of a circle. Third thing is we are going to use properties of chords and diameters to find missing chord and arc lengths. Before we jump into the first theorem, I just want to give us a reminder about what a chord is. We learned this in section 1. A chord is a segment with endpoints on the circle. So looking at a circle, this is a chord. It has one endpoint on the circle and another endpoint on the circle. Remember, a special chord is a diameter. Diameter is just a chord that passes through the center of the circle. So we're just going to jump right in with the first theorem. The first theorem says two minor arcs are congruent if and only if their corresponding chords are congruent. And then there's an example. It says find the measure of arc CA. Okay, so two minor arcs are congruent if their chords are congruent. So we notice we have two chords here. We have chord CB and we have chord AB. They're chords because they're segments that start and end on the circle. And it's really faint, but you can see that the chords are marked congruent. Because the chords are congruent by this theorem, the arcs are also congruent. If the arcs are congruent, I can set their measures equal. So that's what I'm going to do. I have 2x add 48 is equal to 3x add 11. I'm going to subtract 2x from both sides. So I have 48 equals x add 11. Subtracting 11 from both sides, I get x equals 37. But that's not what the question asked. The question specifically asks for the measure of CA. So it's really asking for this arc right here. Okay, so now that I have my x, I'm going to substitute x back in to both CB and BA. Starting with CB, I have 2 multiplied by 37, add 48, which ends up being 122 degrees. Substituting into BA, I have 3 multiplied by 37, add 11, which also ends up being 122 degrees. Okay, well, let's stop right there. Is that coincidence? Let's think about it. No, it should not be coincidence. By the theorem, the chords are congruent, therefore the arcs have to be congruent. They have to be the same measure. So if they did not end up being the same measure, that would have meant that we did something wrong. Okay, so I have two arcs that are 122 and 122, and now I'm looking for arc CA. Well, remember that the entire circle is going to be 360. So I have 360 equals my 122 plus my other 122 plus arc CA. 122 plus 122 is 244. So I have 244, add arc CA is equal to 360. Subtracting 244, I end up with arc CA is equal to 116 degrees. Just as a reminder, this would make it a minor arc. It's between 0 and 180. So that makes it a minor arc. So that was theorem number 1. Now we're on to theorem number 2. Well, two more theorems, I guess, really. First one, if a diameter is perpendicular to a chord, it bisects the chord. So looking at the example we have here, we have a diameter, AB, that's perpendicular to a chord. Because it's perpendicular to the chord, it bisects the chord, cuts the chord into two congruent pieces. The converse is also true. If a chord is if one chord is the perpendicular bisector of another, then the chord is a diameter. So in our case, AB is the perpendicular bisector of FE, It's both perpendicular and bisects. That means AB is a diameter. So we're going to apply both of these in example number 2. Example 2 says, in the figure, DB is equal to 12 and FE is equal to 8. Find the length of FB. Okay, so we're asked to find FB. This arc right here, or this chord. This radius, really. We are told FE is 8, and then we are told that DB is 12. Okay, well, I obviously know that I'm supposed to use the previous theorem. So I have diameter AC. Diameter AC is perpendicular to this chord DB. By the second theorem, because it's perpendicular, it's going to bisect the chord. So instead of being 12, 12 is going to be split into 6 and 6. Now, if I look at this little triangle here, I have a right triangle. I know two sides. I'm solving for the third side. So I'm going to use Pythagorean theorem. I have 8 squared plus 6 squared equals x squared. So this becomes 64 plus 36 equals x squared. 100 equals x squared. Taking a square root, I get x equals 10. So in this case, FB is 10 units. Well, I guess not units, 10 inches. Okay, so that was a little bit of a more basic example. So now we're going to jump into a little bit more difficult example. So flip the page. Okay, so it says, in the figure, DB is 40. FE is 8 less than FB. Find AE. Okay, this one is difficult. So I'm going to start you out. It says DB is 40. FE is 8 less than FB. So I'm going to draw in FB. Okay, FE is 8 less than FB. So I'm going to call FB X. And then FE is 8 less than FB. It's going to be smaller, so I'm going to have to subtract 8, 8 less. So FE is going to be X minus 8. Okay, by the previous theorem, I know that AC is a diameter, and it's perpendicular to a chord. If it's perpendicular to the chord, it's going to bisect the chord. So instead of 40, my chord is going to be cut into 20 and 20. Now, like the previous example, I have a right triangle, and I can do Pythagorean theorem to help me find FB. Right now, pause the video and do Pythagorean theorem. Please be very, very, very careful. Find X and then come back to the video. Okay, let's see how we did. Our two legs in this example are x minus 8 and 20. So I have x minus 8 squared plus 20 squared equals x squared. X squared is just x squared. 20 squared is 400. This is the part that I'm expecting we had a little bit of difficulty with. Remember that to square something means to multiply by itself. So x minus 8 squared is x minus 8 multiplied by x minus 8. So some of you use that term that I'm not going to use. Some of you draw arcs. I like to do the box. So hopefully you remember this since we did it a few days ago. X and x is x squared. X and negative 8 is negative 8x. X and negative 8 is negative 8x again. Negative 8 and negative 8 is positive 64. So I'm going to substitute that back in. I have x squared subtract 16x plus 64 plus 400. Combining like terms, that's x squared subtract 16x plus 464 equals x squared. Now conveniently, the x squareds are going to cancel from both sides. If I add 16x to the other side, I get 464 equals 16x. Dividing by 16, that gives me x equals 29. Okay, but that does not answer the question. The question asks for AE. So what I'm going to do is I'm going to substitute that 29 back into my figure. So I have 29 here, and then FE is x minus 8, 29 minus 8, so it's going to be 21. Okay, now we are asked for AE. We know the FE part, but we still need the AF part. Well, hopefully what you notice is that AF is a radius. So it's going to be congruent to FB. FB is 29, so AF is also going to be 29. In this case, AE then is going to be AF plus FE. That's the segment addition postulate. AF is 29, FE is 21, so I get AE is equal to 50 nanometers. Those were the units we were given in the problem. So hopefully your multiplying and your Pythagorean theorem went well. Again, though, this was a really tricky problem, so if you made a mistake, that's not a big deal. If you have any questions so far, please make sure you write them down so you can ask in class tomorrow. Moving on to our last theorem. It says two chords are congruent if and only if they are equidistant from the center of the circle. Okay, so before we jump into an example, we should probably review what equidistant is. Equidistant is equidistance. Equa kind of sounds like equal. So it means same, and then distant comes from distance. So same distance. So this theorem is really saying two chords are congruent if they are the same distance from the center of the circle. So in the example it says CG equals CH equals 4. So CG is 4, CH is 4, and CE is equal to 5. Find KJ. Well, the first thing that I'm going to notice is that arc KJ is congruent to arc FE. Chord KJ is congruent to chord FE. They are congruent because they are the same distance from the center of the circle. They are both 4 units away, and remember that distance has to be measured with a right angle. So same distance away. So if I can find arc FE, I'm going to know what, if I can find chord FE, I'm going to know what chord KJ is. I'm going to start with this little triangle right here. It's a good one to start with because it's a right triangle and I know 2 sides. So I have 4 squared plus 5, backtrack. 4 squared plus x squared equals 5 squared. So this becomes 16 plus x squared equals 25. Subtracting 16, I get x squared equals 9. So x equals 3. So this little part HE here is 3. Now, how does that help me? It's only part of the chord. I need the entire chord. Well, remember from the second theorem we learned that if a radius or a diameter is perpendicular to the chord, it bisects the chord. In this case, I have this radius. It would be a radius if I continued it. It's perpendicular to the chord, so it's going to bisect the chord. If HE is 3 then, FH is also going to be 3. Now, because FE is the same distance as KJ from the center, they're congruent. So FE is 6, so KJ is also going to be 6 units. And it's split into 3 and 3 also. Okay, moving to example 5. It says, in the figure below, CG is equal to CH. If KJ is 7, find the measure of angle HCE. Use this to find the measure of arc FE. Okay, this is a really tricky one. So I'm going to go through this one with you. Okay, so it says CG is congruent to CH. So CG and CH are congruent. It says KJ is 7. The first thing that it asks is for the measure of angle HCE. HCE. So it's really asking for this angle right here. Well, I got a lot of information. For one thing, I know that chord FE and chord KJ They are the same distance from the center of the circle. So I have these little segments that I know are congruent with right angles. Because the chords are the same distance from the center, so because KJ and FE are the same distance from the center of the circle, they're going to be congruent. KJ is 7, so that means FE is also 7. Next thing, I know that this segment is perpendicular to the chord. Because it's perpendicular to the chord, it's going to bisect the chord. So instead of 7, that's going to be split into 3.5 and 3.5. So this is a good start. Now, this is the triangle that I'm looking at, because I need to find angle HCE. So I'm going to redraw that. So this is HCE. I know CE is 5. I know HE is 3.5. And I need to find this angle. Okay, so this is a little bit of a throwback. I need to think. I have a right triangle. I have two sides, and I'm looking for an angle. Hopefully this brings up some fond memories of trig and SOHCAHTOA. So looking at my angle, 3.5 is going to be opposite. 5 is going to be hypotenuse. Opposite and hypotenuse is the SO. It goes with sine. So I have sine of x equals 3.5 over 5. Remember that sine, cosine, tangent are always taken of an angle. Okay, we talked about how sine and x are in this very happy marriage and you can't just break them up. You need to do something in order to break them up. You can't just divide by sine. Hopefully you remember using the inverse sine on both sides. So that's the one that looks like this. So I'm going to take the inverse sine on the left side. Then I'm going to do it on the right side also. The reason I do this is because inverse sine and sine cancel each other out. And I'm left with x equals the inverse sine of 3.5 over 5, which I'm going to do in my calculator. Please remember to hit second sign. When I do that, I get 44.43 degrees. So in this case, the measure of angle HCE is 44.43 degrees. Okay, so that was the first part of the question. We're still not done. We are now asked to find the measure of arc FE. So now that question asks us to find the measure of this arc right here. So I'm going to draw in this radius. Arc FE is going to be the same as the measure of the central angle. So really I need to find the measure of angle FCE first. Okay, so our angle FCE is angle FCH plus angle HCE. Conveniently, I already know angle HCE is 44.43 degrees. Angle FCH is also 44.43 degrees. So in this case, the measure of angle FCE is going to be twice 44.43. which is 88.86 degrees. Now, if the central angle is 88.86 degrees, the arc is also going to be 88.86 degrees. So that 88.86 is the measure of angle FCE, and it's also the measure of arc FE. Okay, I know that was tricky, and that was a lot of thinking and a lot of throwbacks to things that we have done previously. But I did want to review some of this stuff with you all. So taking a look back at our objectives, we wanted to use properties of congruent arcs. We wanted to determine if a chord is a diameter of a circle. The way we did that is a chord is a diameter if it bisects the chord and is perpendicular. And then we use properties of chords and diameters to find missing chord and arc lengths. So that was the idea that if two chords are equidistant from the center, then they're going to be congruent. So you haven't gotten to do a whole lot of examples on your own. So if you would flip the page, we're going to do some examples for you. As you can see, we have a few extra examples here. Normally these are the examples that would be optional, but I want to make sure that you actually do these examples with me. You haven't done a whole lot of examples on your own, so we need to get some practice. Right now, take a minute or two, pause the video, and do examples 6 and 7 on your own, please. Good luck. Okay, let's see how we did. So for example 6, it says calculate the measure of arc AC. So we need to calculate this measure right here. I'm going to mark it with an X. Right now, we know that arc AB is 116 degrees. We also know that chord AC is congruent to chord CB. Now this is a very important fact. We know that if two chords are congruent, their arcs are also going to be congruent. So if AC is X, CB is going to be the same measure, so I'm going to call it X also. Now, an entire circle is 360 degrees. So I have 116 add AC, which is X, add CB, which is X, equals 360. This gives me 116 plus 2X equals 360. Subtracting 116, I get 2X equals 244. If I divide by 2, I get X equals 122. So I would say the measure of arc AC is 122 degrees. So hopefully you got that one right. Next, let's move on to example 7. It says find the value of X and explain your reasoning. Okay, what we noticed with example 7 is that we have these two little chords right here, and then we have these segments that are perpendicular to the chords. Okay, so I know a few different things. I know that if a segment, like a radius, is perpendicular to a chord, it's going to bisect the chord. That's one thing. I also noticed about these chords that they're both the same length. They're both 12. Well, I know that congruent chords are equidistant from the center of the circle. So congruent chords are the same distance from the center of the circle. That means this length right here is going to be congruent to this length. Congruent chords, same distance. So I have 7x minus 10 equals 3x plus 6. Subtracting 3x, I get 4x minus 10 equals 6. If I add 10, I get 4x equals 16 and x equals 4. So that was the first part of the question, find the value of x. We have to explain our reasoning also. So we have congruent chords. And we know that they are equidistant from the center of the circle. So that's very important. In your classwork, you're going to have a few examples where you have to explain your reasoning. It's important that we know how we got our answer and why that answer is true. So hopefully these two went well. We have 2 more examples and then you are finished with the video. So it says determine if PR is a diameter in the circle shown, and then explain. First thing we should probably recall is how we know if something is a diameter. Okay, a segment is a diameter if it's perpendicular to a chord and if it bisects the chord. So looking at the example to the left, our chord is bisected, so we're looking specifically at this chord SQ. It's bisected because I have one side that's 8 and the other part that's 8 also. So bisected, yes. Now, do I know that PR is perpendicular to the chord, that it forms a right angle? I'm not sure. So I would say PR is not necessarily a diameter. It's because of the previous reason. It could be a diameter, and in fact, if it was perpendicular to SQ, it would be a diameter. But because we're not sure if it's perpendicular, we're not sure that it's a diameter. Okay, last problem is for you, this one right here. You need yes or no, and then you need to explain. I will be checking this when you come to class tomorrow. If you're unsure, go back and watch the video that involves, go back and watch the previous part of this video that involves this theorem. Good luck.